Hello, can you see the whiteboard?
Yes, sir.
Okay. In the last class, we were talking about the decision boundary, and we have seen that uh, if we design or if we define a decision boundary for linear and uh, nonlinear examples, then find we can find the residuals which will affect on the decision boundary. Okay, so initially we have started with a linear decision boundary. Then we have seen that if the data points are given as nonlinear, or the relationship between data points are found to be nonlinear, then for nonlinear data points or nonlinear relationship among the data points, we can have a nonlinear decision boundary. Okay, so today we will be talking about the cost function of the logistic regression, and then we will move on to gradient descent. So let us talk about the cost function. So in the cost function, we have seen that if we use the least square cost function for linear regression, and then we could have the sum of square error, sum of square residuals. Okay, so if we define the error function as j theta, so j theta gives us 1 by m summation over h theta x minus y. Okay, so h theta x minus y square. Okay, so we are taking the square of this deviation or the residuals. So here y is found to be the actual value, and h theta x is found to be the approximated value. Okay, now we get the deviation, we get the residuals between these two readings, and then we take the square of this deviation and we get the sum over it. Okay, for n number of data points. Now, if we use this function, if we use this cost function for logistic regression also, then what happens that the logistic regression, we get the sigmoid function, or we get the nonlinear curve by using this logistic function g of z 1 upon 1 plus e to the power minus z. Okay, so here z is found to be the parameterized data. Okay, theta tx. So when we replace this theta tx or parameterized data in this logistic function or the sigmoid function, then we can see the nonlinear behavior among the data points. Okay, that means this, if we try to fit this nonlinear data in this cost function, or this in this equation of cost function, then what we see that the cost function is found to be non-convex. Okay, the cost function is found to be non-convex. So like this we get the cost function. So here we obtain the g of z. So g of z as h theta x. Okay, h theta x. And if we fit this data in this cost function of linear regression, basically this least square cost function is used for linear regression. Okay, but if we use the same function, if we use the same least square function for logistic regression, then what happens due to this nonlinear data points, uh, we get the cost function j theta as non-convex function. Okay, what does this mean, non-convex function? So in the non-convex function, what happens, we see there are lots of local minima are determined, lots of local minima. So these are the local minima. If we try to if we try to mark each of these local minima, then we can see these are the local minima. Okay, this point, these are the local minima, and this is the global minima. Okay, so every time when algorithm moves onto the optimal value, so every time it get stuck in the local minima. Okay, that means so it will take a large amount of time to converge at local minimum, at global minima. Okay, or optimal value. So therefore, we cannot use this least square error function for logistic regression. So we need to have some other error function, so which will give the convex function. The error function to be the convex function. Okay. So in the convex function, what happens? We see there is only one. There is the global minima, and which can be reached through this gradient descent much more quickly than non-convex function. Okay, so if we see the non-convex function, there are a number of local minimas which are determined using this least square function. Okay, but if we use some other cost function, then some other cost function for logistic regression, then uh, we can have a function which may like the convex function. Okay, so in this convex function, we can reach to the optimal value or reach to the global minima so quickly that there will be no local minima where we get stuck for very frequently. Okay, so here we can use to get the optimal value, so we can use the gradient descent. Okay, gradient descent, that means with gradient descent what we can do, we can estimate the parameters. Okay, so we can estimate the parameters by minimizing an objective function. So if this logistic regression function is found to be an objective function, then we have to minimize that function for n number of points, since we are dealing with n number of points. Okay, so therefore if we need to find, or if we need to minimize the objective function, then we need to minimize this logistic regression function. Okay, so logistic regression function will be minimized for n number of points. Now if we use different functions for logistic regression instead of using least square function, then we can see there is a so instead of using the least square function, we can use some other function, like if I say that z theta would be minus log of h theta x. Okay, for so y equals, that means if y equals to 1, then we can use minus log of h theta x. Okay, and when y is found to be 0, if the level is 0, then we can get another function, so which is minus 1 minus log of h theta x. Okay, let us use this function, and then we see how this function is found to be appropriate for logistic regression. Okay, now suppose y is found to be 1. If the level is positive, then how this function will behave? Okay, suppose this is our 0 origin and this is 1, and we get the error function to be plotted like this. Okay, so this is our j theta. Okay, this is our h theta x. So along x-axis we represent the approximated value, h theta x, and along y-axis we represent the error. Okay, j theta. Now when we have y equals to 1, then we can get the error function uh, like this curve. Okay, now if the cost is found to be, let us consider the cost is found to be 0 for y equals to 1 and h theta x equals to 1 was 1. Okay, so h theta x1 means we can use the first function. Okay, y equals to 1 means we can, if we use the first function, then minus log of h theta will give us 0. 0 means the approximated value as well as the actual value are found to be same. Okay, so in that case the cost will be found to be 0. But let us consider another fact where y is given as 0 and h theta x is found to be 0. Okay, so in that case what will be the cost function? What will be the cost function? Or let us consider y equals to 1 and h theta x equals to 0. So what would be the cost function in this case? So we can use, if we use the first function minus log of h theta x for y equals to 1, then we can have the infinite value for cost function. That means the cost function tends to infinite. Okay, tends to infinity. That means the cost function is found to be some in, so which cannot be determined. So here the cost function cannot be determined. Okay, because cost is found to be, cost tends to infinity for y equals to 1 and h theta x equals to 0. Okay, that means this when the curve is found asymptotic to 1, then we can get this curve. Okay, so this function or this curve is found to be asymptotic to 1, but this will not give any value. That means that for this cost function the cost is found to be infinite. Okay, wait, I'm just coming. ঠিক আছে। So we get this function for minus log of h theta x. Okay, so we get this function or we get this curve for minus log of h theta x when y is found to be 1 and h theta x is found to be 1. Okay, now how to So originally, if we see for log x or for log of h theta x or log of z, then we can see, so this curve will look like this. Okay, this curve will look like this. This is your 1 and this is 0. Okay, now we are taking minus log of h theta x, and because of this, so this curve will look like it is asymptotic to 1. Okay, so when the class level is found to be 1 and h theta x is found to be 0, then that means when the h theta x tends to 0. Okay, or otherwise we can say that h theta x tends to 0. So when h theta x tends to 0 and y is found to be 1, then cost function will give us infinite value. That means the cost will tends to infinity. Okay, so how it is possible? If we consider the same problem that we have discussed in the last week, that if we have a number of examples for tumors, then h theta x tends to 0 means the tumors are found to be tumors are found to be when you quantify the tumors, then the approximated value is found to be 0 or tends to 0. Okay, so in that case the error will be found to be infinite, but this is not possible. Okay, so when for h theta x, when h theta x tends to 0, the cost function is found to be infinite. Okay, and the cost function is found to be infinite, so in that case the tumor will be labeled as malignant. Okay, tumor is labeled as malignant tumor. Okay, so this is not possible. So in that case the penalty will be very large, or penalty cannot be determined. Okay, so if we consider the y equals to 0, h theta x equals to 1, then what happens? So for a y equals to 0, we can use the second equation, minus 1 minus log of h theta x. Okay, and when this will be found, then cost will be determined as 0. Okay, cost will be determined as 0. So when the cost will be determined as 0, that means for class level 0 and approximated value to be determined as 1, the cost function will be found to be 0. When y equals to 0 and h theta x equals to 0, so what does this mean? That means that h theta x tends to 0, or it is found to be 0 when the class level is 0, and for for these two combinations the cost function will be found to be, so we can write the cost function j theta minus 1 minus, so log of 0 means we will have infinite value sum. Okay, so in that case the cos theta will give us j theta equals to minus 1 minus infinite. So this would be appropriate to use this function when we deal with logistic regression. Okay, or sigmoid function. So when the sigmoid function, when we feed the data for logistic regression in this cost function, then we can see that when y is found to be 1, then we can use the function minus log of h theta x. When y is found to be 0, we can use another cost function. Okay, which is found to be minus 1 minus log of h theta x. Okay, and if we add both these functions, that means if we think about if we think that the first function is the probability or probability over h theta x, and the second function is second function is determined as the probability of 1 minus log of h theta x, then if we add both this probability, then the function will give us 1. Okay, that means sum of both this probability will give us 1. Now when the y is found to be 1, then we can use the function minus log of h theta x, and for y equals to 0 we can use the second function minus 1 minus log of h theta x. Now does this function will give us the optimal value, or if we use these functions, can we minimize the errors, or can we quickly get the optimal value, or can we get the uh, can we quickly get the global minimum? Okay, so in that case, we have to introduce the optimization algorithm or optimization technique by which we can get the optimal result quickly. Okay, or we can get the global optima by computing the gradient in the right direction. Okay. Now to get the idea about gradient descent or the similar optimization algorithm, so we need to be introduced with some basic idea about the Taylor series, and how to minimize and maximize the functions. If the functions is linear, if the function is quadratic, if the function is cubic, if the function is quadric, then how to use those functions as objective function and get the minimum or maximum value of the functions. Okay, so if we consider okay, let us start from the Taylor series expansion for three terms. Then we will see how this Taylor series expansion can be used to optimize a quadratic as well as cubic functions for getting the error minimum. Okay, so you all are familiar with this Taylor series expansion of three terms. So we can write f of x plus del x equals to fx plus del x. So derivative of f with respect to derivative of partial derivative of this is the partial derivative of f with respect to x. Okay, and the third term would be half of del x square del 2f by del x2. Okay, so this is this Taylor series. This Taylor series expansion is familiar to us, so we know about this Taylor series. So if this is a single point, then we could expand the Taylor series by having this interval del x, and this will be found to be multiplied with the first order derivative as well as the second order derivative. So if we have the second order derivative, then in that case we can have this interval squared. Okay, so for the first term we can see the fx, and the second term is del x, uh, and the partial derivative del f with respect to x. Okay, del f by del x plus half of del x square, then del 2f by del x square. Okay, now let us consider here x is n number of points, so x1, x2, xn. Okay, instead of taking a single point, now we are taking a set of points, okay, from x1 to xn. Now in that case, if we write the Taylor series expansion, then we can write this Taylor series expansion as fx plus, so this del x becomes a vector. That is why we are writing del x transpose del xt. Okay, and this del a by del x turns to be a gradient. So we can write gradient of fx. Gradient of fx. Okay. So this gradient of fx is also a vector. And half of del x t, okay, del x t, and instead of writing del 2f by del x2, we are writing h, and then we are writing del x. Okay, del x. So here del xt is the vector. Okay, when we are considering when we are considering n number of data points, then for n number of data points the Taylor series expansion will be found as fx plus del xt, then gradient of fx. Okay, then this del f by del x del f by del x becomes gradient of fx. Okay, and plus half of del xt into h into del x. Okay, so this is the Taylor series expansion for n number of points with three terms. Now what is h here? So h can be labeled as Hessian matrix. So we can say this is Hessian matrix. And here del f x is nothing but del x del f, okay, del f1 by del x1, del f2 by del x2, del fn by del xn. So this is our grad of fx or gradient of fx. Okay, so that is why this is I have already said that this is this gradient of fx is a vector. Okay, so in this vector for individual points from x1 to xn, we can have the partial derivative of partial derivative from f1 to fn with respect to x1 to xn. Okay. Now, here h j k is found to be del 2 f del x j del x k. So since this Hessian matrix is found to be symmetric, therefore we can have the same vector by changing the rows into column or columns into rows. Okay, so therefore we can write hjk equals to hkj. Okay, and this will give the same matrix. So we can have this same matrix since this is the symmetric matrix. So therefore we can both these notations for representing the Hessian matrix. Okay, now let us consider we are writing f of x plus del x equals to fx plus j of del x. Okay, now we are saying this j. So since this is considered for the second term del x, so this second term del x del f divide del x by del f by del x. Okay, now we are saying instead of writing the del x we are writing j, or we are writing j for this partial derivative. Okay, and we keep unchanged the del x. Now we why we are considering this I will tell you later, but for now we are considering f of x plus j of del x. Okay, so instead of writing this partial derivative del f by del x, we are writing j. Now what is j here? J is the Jacobian matrix. Jacobian matrix. Now, if we consider n number of points, then we can get this Jacobian matrix. Otherwise, this Jacobian matrix will turn to be a single value when we have a single point. If we consider the single point, then we could get this Jacobian matrix will turn to be a single value instead of a matrix. Okay, but for n number of points, we can get this Jacobian matrix as well as this Hessian matrix for third term, for second as well as for the third term. Okay, now let us consider, since we are talking about the minimization of an objective function, so therefore if we write 0 on the left hand side, and then we are writing f of x k, f of xk plus j of xk. Okay, then we are writing x of xk plus 1 minus xk. Okay, so since we are trying to minimize some function, we call this is the objective function, then this function, we can get this function as f equals to 0, or better to write a capital F equals to 0. Okay, now in this capital F, we can have f1 equals to 0 if we consider n number of points, f2 equals to 0, and fn equals to 0. Okay, so for n number of points, so that means there will be n variables, there will be n variables and n number of objective functions and n number of objective functions. Okay, now if we consider to minimize this n number of objective functions individually or independently, then we can get this capital F of 0 for n number of variables. Okay, so there are n number of variables and n number of objective functions. Now to extend this convention for or we can if we consider a single point xi. Okay, so we are not considering the uh, here we are not considering two different variables, so we are working on a single variable. Okay, and if we have such n number of variables, then for n number of variables we can have n number of objective functions, and we need to minimize this n number of objective functions in terms of f equals to 0, capital F equals to 0. Okay, that means independently we have to minimize this n number of objective functions from f1 to fn. Okay, so for that we can write f1 equals to 0, f2 equals to 0, fn equals to 0. Now we get back to the equation for a single variable or one variable, where we minimize the function f equals to 0, and we are writing the 0 on the left hand side, then we are writing f of xk. Okay, plus we are writing the Jacobian matrix. So since there are n number of points, but for getting getting this minimum value, or to minimize this function for a particular point xk, then we can write 0 equals to f of xk plus j of xk, which is multiplied with xk plus 1 minus xk. So what is k here? K denotes the iterations. Okay, so here k denotes the iterations. Okay, now if we rearrange, so this is nothing but the del x, xk plus 1 minus xk. Del x or interval, this is called the interval between xk plus 1 current point and the next point. Okay, so if we rearrange this, let me write jxk into xk plus 1 minus jxk into xk. Okay, now we get these two terms on the other side, or if we take this term on one side and get remaining two terms on other side, then what we can have, we can have j of xk into xk plus 1. Okay, and here we get j xk minus f of xk. Okay, minus f of xk. Now we can write xk plus 1 equals to xk minus f of xk divided by j of xk. That means we divide right hand side as well as left hand side by this Jacobian matrix jxk. Okay, at point xk. So if we rearrange this equation, then we can write xk minus jxk inverse, which is multiplied with f of xk. Okay, so this is, so for this equation we can write x k plus 1 equals to xk minus j xk inverse f of xk. Okay, now if we consider this equation, then how this equation will serve to optimize a function when we have n number of points, or if we consider for a single point, or if we consider a quadratic equation like x square minus 9 equals to 0. This is our fx. Okay, we can consider this equation fx equals to x square minus 9. So we have to minimize this function and to get the value for x. Okay, so our objective function is a quadratic equation fx equals to x square minus 9. We have to minimize it. Okay, so we can write x square minus 9 equals to 0, and we have to find so initially we can see from this equation that this will give x equals to 3. Okay, so 3 would be one value. Then we can look for another values if we can get from this derivation. Okay, so we can write now xk plus 1 equals to xk minus. So what would be the, if we go for first order derivative for this objective function? So del
2x.
Del of x square minus 9.
Yes,
Okay,
sir.
okay, then what we get?
It's a 2x.
2x. Okay, very good. So we get the 2x. Okay, and here we are writing xk plus 1 equals to xk minus j of xk inverse. Okay, then f of xk. Now in place of inverse jxk inverse, so what we can write? 1 by 2xk. Okay,
Yes,
so
sir.
1 by 2xk, and then here in place of f of xk, what we can write? We will write xk
K
square
square minus 9.
minus 9.
Yes, sir.
Okay, now let us solve this equation. So now what we do? So okay, so here we can get 2xk square minus we will get here half of xk. Okay, then 9 by 2. Okay, so here we get, yeah, 9 by 2. What we get here?
Sir, sir, we are
This
getting here.
divided by 2xk.
Yes, sir.
So here we will get,
Sir, half minus half xk square.
no, minus plus 9.
Yes, sir. Sir, 2xk square minus half xk square.
2x square minus,
Half x square.
no, here we will not get half x square. Here we will get this 9 will be multiplied with 2, 18, 18xk, or 9 by 2. 2x square, 2xk square minus half of, why half of, okay, xk, and this is, okay, let us not in this way, we can have xk minus half of xk square minus 9 by 2, 9 by 2 xk. Okay, 9 by 2 xk. So 9 by 2 into 1 by xk. Now here so half can be taken as common. If we take the half common, then what we get? Okay. We are getting it wrong. 2xk square minus xk square plus 9 divided by 2xk. Is that okay for you?
Yes, sir.
Okay. So 2xk square minus xk square plus 9 divided by 2 into xk. Okay. Now if we subtract, let us subtract 3 from both right hand side and left hand side. Okay, then what we get? 2xk square minus xk square plus 9 divided by 2xk minus 3. So what it will give us? 2x 2xk square minus xk square plus 9 minus 6 xk divided by 2 xk. Okay, so now you will get, okay, let 2xk common, and then we get this equation as xk
xk minus
square,
3 whole square.
xk minus,
3 whole square.
yes, xk minus 3 whole square. Okay, so from this equation, so what we are getting, so other values can be determined from this equation. So
Yes, sir.
one value would be 3. So what would be the another value? Okay, so what would be the another value from, so we can get another value from this equation. So finally what we get, xk plus 1 minus 3 equals to half of 1 by xk, which is multiplied with xk minus 3 square. Now what we do, we use this minimization function to get the next value in terms of the present value or the current value. Okay, so here xk plus 1 is the next value. Okay, so for k plus 1th iteration we will get the function value at xk plus 1. Now what does this mean? Let us consider. So if we let us consider, we have started from here, and for every step or for every iteration, so we get a we travel a small distance. Okay, we travel a small distance. So distance means it may be the steepest distance. Okay, maybe the steepest distance, steepest descent. If we term as steepest descent, then we can take this small step and get this optimal value. Okay, and get this optimal value. So here we get the optimal value. So this is called the global minima. So that was only determined for x k plus 1. So we can similarly we can get x k plus 2, x k plus 3. Okay, up to x k plus n. So we will start from x k plus 0. Okay, so there are n number of variables. For n number of variables, so we can get this steepest descent, and we can converge quickly by getting this gradient over n number of points. That means, as I said earlier, that we are trying to minimize the given objective function in terms of gradient or slope of this curve. Okay, so f of, so here this is called the gradient of f of x. Okay, so gradient of f of x is nothing but the partial derivative del f1 by del x1 to del fn by del xn. This is a vector. Gradient of fx is a vector of partial derivatives over n number of points from f1 to fn with respect to x1 to xn. Okay, now how can we use this function to function in optimization algorithm? So we can have the first optimization algorithm, which is called steepest descent. In the steepest descent, we get the function to be optimized as xk minus, here we use delta of what we can write. So we can write here, okay, Jacobian delta of Jacobian of